Greetings to all. My name is Tuna. In this video, I will discuss two topics from ME210 course. First, I will start with parametrization of curves and surfaces. Then I will dig into integral theorems of vector calculus. Let's start with curves and surfaces. Why are we interested in curves and surfaces? Because they show us some real-life actions like moving particle paths, and we can make calculations with them. Okay, let's start with curve. How we parameterize a curve. We can use a vector valued function with only one variable. And this is an helix example from GeoGebra. Let me explain it visually. This is Burak Hoca's parabola file on GeoGebra. So we have a vector r equals ti plus t squared j. Okay. I component gives us the x values and j component gives us the y values. As you can see or guess from here, y equals x squared. So this vector gives us the curve y equals x squared. And you can see the r vector is tracing when I change the t values. So this is the idea. It traces the parabola. This is how we define curves. But there's one important note here. This is not the only way how we can define this y equals x squared. There's infinitely many ways to write it. Okay, let's move on to surfaces. Now let's move on to surfaces. Let me clear screen. How we can define surfaces? This time we need two variables. We can expand the idea of curves here as well. We can use some tricks and consider one of the variables as constants. For example, let's take v equals 3 and play with u here. If you play with u, assume that this is the curve. When you play the u, you will trace a curve with one variable. You're changing only one variable. Then change to v equals 5, for example, here. If you keep doing this, you'll see that you are tracing the surface here. And there you go. You have a surface. And that is how we define surfaces. Similar to curves, as well as in curves, you can define them with infinitely many different ways. They're not unique. So we learned how to define curves and surfaces, and we can do some cool stuff with them. The second topic of this video is integral theorems of vector calculus. We have three theorems: Green's theorem, divergence theorem of Gauss, and Stokes theorem. So let's start with Green's theorem. Green's theorem has two forms, curl and divergence form. Let's start with curl form. If you want to find the curl in a region, you can do this by simply this double integral curl integral on the region. Or even simpler, you can take this cyclic integral around this region. You can take this curve C integral. If you know u and v, you can do that. You don't need to get into the region. And on the divergence form, you want to find the divergence in the region, you can simply do that cyclic integral. The form changes, obviously. This is the curl form. This is the divergence form. Can we do that on all regions? Unfortunately, no. For this theorem to hold, the boundary curve should be simple, non-self-intersecting, and oriented such that the region R remains to its left, and it should be connected. The second theorem, divergence theorem of Gauss. If you find the divergence of a volume in a volume, you don't need to calculate this integral. You can just calculate the surface flux integral, this double integral here. It is the similar idea with Green's theorem. You don't need to get into this volume. You can do it by the surface around it, surface that bounds it. Can we do that on every volume? Unfortunately, no, again. For this theorem to hold, the boundary surface should be closed, orientable, and connected. Also, the vector f vector and its partial derivatives should exist in the volume and at the boundary surface. The last theorem, Stokes' theorem. This is the 3D version of Curl's form of Green's theorem. We had a region in Green's theorem. Now the region is a surface here in Stokes' theorem in 3D. We have calculated the cyclic integral here, and we calculate the cyclic integral that bounds the surface again here. The only thing that's changed region is now surface, dx dy becomes ds, and k, this is not a constant anymore, this is changing, this is n, okay? Again, we have some restrictions. For this theorem to hold, the surface S should be piecewise smooth and orientable. The boundary curve C, simple, non-self-intersecting, close and piecewise smooth. So these are the restrictions. And that is all for this video actually. And these are my references. And thanks for watching.